So in our last problem, the way that the information was given was that one piece of information was an exact multiple of another piece. Mike was exactly 2 times as tall as James. But that's not the only way that information can be compared, that quantities can be compared. Let's take a look at a different type of problem. The combined weight of James and Julian is 56 pounds. If James weighs 4 pounds more than Julian, what is Julian's weight? So in this case, the weights of James and Julian are not compared in the sense that one is an exact multiple of another one. In this case, all we know is that James weighs 4 pounds more than Julian. So again, we start the first stage of the model drawing process by just drawing a diagram that accurately represents all the information in the problem. We've got 2 quantities. We've got James's weight, we've got Julian's weight, so we're going to have a bar that represents each. In this case, we know that James weighs 4 pounds more than Julian, and that's the only comparison we have between their weights. So we're just going to draw a bar that James's bar is a little bit longer than Julian's. So we might draw a bar like that for James, and a slightly shorter bar to represent Julian's weight. Now, we can actually do a little bit better than this, right? Because we know that James weighs 4 pounds more than Julian. So we actually know that James's bar is 4 longer than Julian's. Now, there's a couple of ways we can represent this. It's going to turn out to be more useful if we kind of cut James's bar off where it looks like Julian's ends, and then we put a 4 in the extra part. This represents that James's bar, James's weight in this case, is 4 more than Julian's. And the last thing we have to do is put a question mark on the diagram to represent the unknown. If we read the last sentence of the problem, the question is asking for Julian's weight, so we are going to have a question mark there. Again, as we did last time, we can check to make sure that we have an accurate diagram simply by, can we recreate the problem just by looking at our diagram? In this case, we can. It's clear that James weighs 4 pounds more than Julian, and that we're interested in Julian's weight. Ooh, actually, I made a mistake, right? Catch me. The combined weight is 56 pounds, and that's not on the diagram anywhere. So I would need to put that over on the side to denote that the length of both bars combined is 56. Thanks, Mike. So now we have a complete diagram. And stage 2 of the model drawing process is that unit sentence that we talked about before. But in a problem like this, the unit sentence is less clear than it was before. In our previous problem, every piece was a unit because every bar was exactly the same size. That's not the case in this problem. So we have to be a little bit clever in how we find our units. So you can see now, if you look closely enough, why I chose to depict James being 4 pounds more than Julian in this way. If you look at the first part of James's bar before the cutoff, and maybe I'll shade it to make it a little clearer, we are looking again for units, and remember, units are pieces of the diagram that are the same size. The first part of James's bar is exactly the same size as Julian's entire bar. So that's where we're going to find our units. The 2 shaded pieces in this problem are actually units because they're the same size. Now, we have 2 units. The tricky part is, what is 2 units identical to? 2 units is not the same as 56, right? 56 is the length of both bars combined. But the shaded parts are not both bars combined. What did we have to do to get to the shaded part? We actually had to kind of chop off that excess 4 from James's bar to get 2 units. So actually, 2 units isn't 56, 2 units is 56, which is the length of both bars, minus 4, 52. We might, as teachers, write in 56 minus 4 so our students can see exactly where that 52 is coming from. Because again, the first time you see this, it's not obvious. You have to look pretty carefully. Nevertheless, once we get that unit sentence, like we mentioned last time, the problem is for all intents and purposes over because we can rely on our knowledge of partitive division in this case and multiplication if necessary. It's actually not necessary in this case to solve the problem. If 2 units is 52, partitive division tells us that 1 unit is equivalent to 52 divided by 2, which is 26. And it turns out in this case, that's exactly what we're looking for, right? Julian's bar represents 1 unit. We figured that 1 unit is 26. So as our complete sentence answer, we would write Julian weighs 26 pounds. Incidentally, it's always a good idea to check our work. So once we get an answer, we can make sure that this answer makes sense. We can take our answer, kind of plug it into the problem, and make sure that everything comes out. In this problem, James weighed 4 more pounds than Julian. So if Julian weighs 26 pounds, James is going to weigh 30. Their combined weight is 56. That adds up. James is 30, Julian's 26. 30 plus 26 is 56. So the last two problems we've seen have illustrated the two ways that two pieces of information can be related to one another. In one case, you can have the bigger piece of information, the bigger quantity, be an exact multiple of the smaller quantity, or, as in this problem, the bigger quantity can be a certain amount more than the other quantity. The last problem we're going to look at actually combines both of the last two types of problems in one problem. In this problem, Mike, Wendy, and James are pooling their money to buy an air conditioner. Wendy contributes 3 times as much as James, and Mike contributes $30 more than James. If they contribute $215 altogether, how much did Mike contribute? So you can see again that Wendy contributing 3 times as much as James is similar to our first problem in that the amount she contributes is an exact multiple of the amount James contributes. On the other hand, Mike contributing $30 more than James is similar to our last problem, where we have that one quantity is a certain amount more than another quantity. Our first stage, again, of the model drawing process is just to draw a picture that represents the situation. In this case, we have 3 quantities. We have the amount of money contributed by Wendy, James, and Mike. So we're going to have a bar for each of these people. Let's label them accordingly. And now we need to draw bars that represent their contributions. The first part of the second sentence reads, Wendy contributes 3 times as much as James. So again, what this means is that her bar needs to be exactly 3 times as long as his. So if we draw a bar to represent how much money James contributes, then Wendy's bar needs to be 3 times as long as this, so it needs to be 3 of these pieces. So what we have drawn so far represents the first part of the second sentence. Wendy contributes 3 times as much as James. The second part of the second sentence says Mike contributes $30 more than James. So all we know is that Mike's bar is going to be a little bit longer than James's, but we don't know if it's a certain multiple of James's. We're not given that information. All we're given is that Mike's bar is going to be 30 longer than James's. So we might do something similar to what we did in the last problem. Draw Mike's bar longer, cut Mike's bar off where James's ends, and label the excess part 30. Again, the question's asking how much Mike contributed, so we're going to have a question mark at his bar. I am not going to make the same mistake I made in the last problem. They contributed $215 altogether. We need that information. And we are again going to put a bracket on the end to signify that the length of all of the bars combined is 215. Again, this is a complete diagram. We can completely recreate the problem just by looking at the diagram. We don't have to read the words. Second stage of the process, as it has been, a unit sentence. Some number of units is identical to some number. And we do see units in this problem because James and the pieces of Wendy's bar, the boxes in Wendy's bar, are exactly the same length as James's box because Wendy contributes exactly 3 times as much as James. So all of these pieces are unit. Mike's bar, however, is not exactly the same length as any of these, but as we saw in the last problem, the first part of Mike's bar is the same as Wendy's and James's. So again, if we shade to illustrate this, we see that in this problem there are actually 5 units represented, right? Wendy's 3 units, James's 1 unit, and the first part, the front part of Mike's bar also represents 1 unit because again, remember, units are pieces of the diagram that are the same size in more than one place. So there are actually 5 units here. The tricky part, as it was last time, is determining what are 5 units actually equal to. 5 units is not the same as 215, right? Because the 215 represents the lengths of all of the bars combined. But the 5 units do not represent the lengths of all the bars combined, right? How do we get to 5 units is we have to cut off the end of Mike's bar, right? So if we chop that 30 off, then we've got 5 units. So chopping that 30 off corresponds to subtracting 30 from the 215. So 5 units is in fact 215 minus 30. And again, as we've seen in the previous problems, we could just do that subtraction and get 185. As we've seen in the previous problems, as soon as we get this unit sentence, the problem is for all intents and purposes done. Because partitive division and models of multiplication are going to take us down to 1 unit and up to as many units as the question asks for. So again, hopefully students that understand and were taught partitive division will understand that if 5 units is 185, then to figure out what 1 unit is, we need to divide 185 by 5. You also, as a teacher, have opportunities to set up problems in such a way that you can test whether your students know mental math strategies, or if you want them to perform the algorithms, you can give them different types of numbers that would achieve either of those goals. With 185 divided by 5, we might use mental math strategies. We might use compensation. We could multiply both of those by 2. We could use the distributive property. Either way, we can see that 185 divided by 5 is 37. And then we look back at our diagram and we ask ourselves, how many units are we interested in? In this case, it looks like we're interested in 1 unit. Mike's bar is 1 unit plus another 30, right? So if 1 unit is 37, Mike's bar is 1 unit, 37 plus 30, and that's our answer. So in this case, Mike's bar is 67, and we would answer the question with a complete sentence. Mike contributed $67. One thing to notice in these problems is it's completely arbitrary what I asked for in this problem. I could have asked how much did Wendy contribute. I could have asked how much did James contribute. I could have asked how much more did Wendy contribute than James, etc., etc. But hopefully the one thing that we notice is that if we solve these problems in the same way with these unit sentences, we can see parallel algebraic solutions, at least as teachers. And these are the solutions that we're going to want our students to be able to come up with when they get to middle school and high school. We're not going to want them to solve word problems using bar diagrams in high school. We want them to use algebra because it's the most efficient way to solve problems. But you can see that these unit sentences really have a nice parallel to algebraic equations, and that's the idea. In later clips, we are going to use the model drawing process to solve word problems involving fractions, ratios,